Assalamu alaikum everyone. I am Samir Afrid and today I am going to present you our MATLAB project app 2D heat equation solver by FTCS method. Understanding transient behavior of heat transfer in 2D material is challenging, and this app will help us to visualize how temperature gradients drive heat flow over time and will help user to understand the relationship between thermal diffusivity and speed of diffusion. Now let's get started. Here in the app interface, we got two portions. This is the input interface and this is the output interface. For input, we need object details, discretized domain, and initial condition, boundary condition. For output, we will observe heat flow animation, contour, and 3D surface plot. So we need length and width of the surface. Let's take 10 each. For diffusivity, we have multiple options. We can use diffusivity of copper directly here. Now I will choose one as diffusivity. For step size, we will take 0.1 each, and for time step it will be 0.001. We will observe the animation up to 3 seconds here. As initial condition, we can write our equations here. We also have options for Gaussian and center block. We'll use this. Now we have to put our boundary conditions. This will be 100. Okay. For corner points, we will take 300 each. Now if we run the simulation, we'll give this interface. Here the center block is the temperature block of 500 units and the surrounding is 0 unit of temperature. Now if I play the animation, so done. Now if I decrease the speed and so what's happened here, as we can see, the heat is diffusing towards the cooler surroundings, and almost after 1 second we can see the yellow portion is totally disappeared and this greenish part is left, which is actually 300 units of temperature. And as the time goes on, after 3 seconds we can see the total heat, is dissipated around all the surface. Now we will watch contour plot. Here we can see these are the contour lines, and we can see lines are getting denser here. This tells us how rapidly temperature changes around this region. If we look at the boundary conditions, we may see for left and top boundary we took 100. So these are the higher temperature region compared to these two. That's why temperature dissipates much faster here. We can also see coordinates at temperature at different coordinates. Here for x is equals to 3.8 and y is equals to 8.6, we will see temperature is 124.839 unit. At center there is 201.101 unit of temperature. Now let's move to the next part. So in surface plot, this is what actually we got from 2D visuals of heat flow animation. These are two knobs which can be used for rotating our graph. Now we can also rotate it from here. Now if we see this, this is what actually you got in heat flow animation at the final time. These are the x and y axis, and z is the temperature. We can observe temperature at the various region and how temperature changes with the time here. Now let's change the time. Let it be 0.01 so that we can see what the graph looks like at initial time. If we run the simulation, this is what actually we give input. Yes, this is the center block that we give input as an initial condition, and we can see the graph here. Now if we take another example, let's say diffusivity is 0.5, 0.2, true, and the initial condition, we will input initial condition here. This will be 200. For boundary condition, we will use an equation. This is another plot. Let's, if we increase the speed, let it be 3. Now let's see the animation. Here we can also see the heat dissipates as the time goes on. We can see the contour plot here, and this is the surface plot. Now, if we watch, this is what it looks like at initial condition, at initial time. Now, if we change the y step here, let's say 0.01. So this will give us a stability warning. The app gives us 4 different options to solve the issue. Here it says alpha should be less than 2.48. So let's decrease the diffusivity. If we take silver, this will be fine. Now you can see our simulation will now happen again. Oh, let's change the final time. So as we can see, as diffusivity is very low, the heat dissipation is happening very slowly. So that's all. Thank you very much.